Hello and welcome to this video lesson. Here we are going to review trig ratios in terms of math a little bit and then talk about how they can be applied in simple physics situations. In this video, we'll do a very quick review of trig ratios, and then from there we'll talk about why they are important in physics and how they could be used in different ways in physics. So first of all, trig ratios apply to right angle triangles. So in this case, we have two triangles. One is black and one is blue. You can see they both share the same angle over here. This angle is 36.899. This angle over here is 90, this one is 90, and that would mean that this angle for both of them are the same because the angles in a triangle make 180. So 180 minus this minus 90 will give me this, and 180 minus this minus 90 again gives me these. So these two angles are also the same, meaning that these two triangles are actually similar triangles. I'm going to make an assumption that you don't know what a unit circle is and you don't really know what trig ratios are yet. So I'm going to introduce you to these trig ratios that exist. Trig ratios, and this is degrees, we have three of them. We have more than three, but these are the ones that we're going to focus on. We have tan of an angle, we have cosine of an angle, and we have sine of an angle. So let's talk about tan of an angle first. So tan of an angle, we're going to be looking at this angle over here. This is 36.8699 approximately. There's more digits, but this is what we're going to leave our values at. And we're going to put that on our calculator, and we're going to see what we get when we put tan of 36.8699. And assuming that our calculator is in a proper mode, and proper mode meaning it's in degrees, then we should get approximately 0.75 here. We're going to do the same thing with the other ones. We're going to do cosine of 36.8699, and when we do that, we get 0.8. And when we do the sine of this one, 36.8699 degrees, we're going to get a value of 0.6. So these are stuff that we can just put on our calculator. And again, I'm not doing a whole video on what these functions mean in a lot of detail. This is just a very quick review for those of you who might have missed it, and we'll give you a little bit of information about what these things actually mean. So talking about tan of this angle is going to equal to 0.75. What does that mean within a right angle triangle? So the tan of an angle always gives us a ratio, and it gives us a ratio of the opposite side. So if this is my angle, the opposite to it will be this one over here, and the hypotenuse would be the big one over here, and the adjacent is something that's attached to it. So in this case, there's two sides attached to this. Since this already has a name, it's the hypotenuse, then this is going to be our adjacent. So I'm going to label those. So here's our angle. Adjacent to it is over here. Our hypotenuse is the longest side, and this one over here is going to be the opposite. So the tan of our angle then, so the tan of an angle will equal to the ratio of the opposite side divided by the adjacent side. So opposite over adjacent. So in our example there, we have our opposite for the black triangle is a 3, and the adjacent is 4. And that's going to 3 divided by 4 is 0.75, and we can see that's consistent with this. If I were to take this angle, it would be 0.75. And if I were to take the tan of an angle is always the same value. So if I have a different triangle, it should have the same ratio. So O over A for blue, the opposite side is 6, the other one is 8. That's also 0.75. So you can see that these are all consistent. For cosine of an angle is going to equal to the adjacent, or it's the ratio of the adjacent over the hypotenuse. So for the black triangle, the adjacent side is 4 and the hypotenuse is 5. And if I divide 4 by 5, I will get 0.8. And if I do it for the blue triangle, I will have my adjacent side is 8 and my hypotenuse is 10, and that will give me the same ratio, 0.8, and it should. And you can see that these are all consistent as well. Finally, for sine of an angle is always the ratio of the opposite side over the hypotenuse. The opposite side for the black triangle is 3, the hypotenuse is 5, and that will give me 0.6. And for the blue triangle, opposite over hypotenuse, the opposite is 6, and the hypotenuse is 10, and that's also 0.6, so those are all consistent. So when you're thinking about it, whenever you think about 10, for example, 10 is always the ratio between the opposite and adjacent. So if your triangle is this small, then opposite over adjacent will always, if the angle is 36.887-ish, approximately this one, will always be 0.75. So if you divide this side by this side, 0.75. This side by this side, 7.75. This by this, this by this, this by this, it will always be 0.75 as long as your angle is 36.8699. And same thing for the sine, always opposite over hypotenuse, and cosine always adjacent over hypotenuse. So there's a little shortcut for knowing this. For those of you who have, you sometimes might be forgetful, you can always use the expression so, ka, to, a, and we got our sine, cosine, and tangent. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. So how is this going to be helpful? Actually, we're going to do a little bit more math here. I'm going to leave this SOHCAHTOA here, and let's say we have a right angle triangle. Remember, you can only use this whenever you're using right angle triangle. And let's say you have, let's say we want to figure out what the angle here is. We have this angle, we're going to call it theta. And let's say this side over here is 4, and this side over here is 6. We can obviously find this side over here. We can use Pythagorean theorem, but we don't need to because we already have, here's our angle. So this is opposite. This is the hypotenuse because it's the biggest side. So whenever we have two things, opposite hypotenuse, to figure out what the angle is, we're going to use sine theta is equal to that ratio, the ratio O over H, which is 4 over 6. So in order to find that theta angle, we are going to use an opposite operation or an inverse operation to sine, and that is called the inverse sine. So I'm going to do that. So inverse sine, so theta, sorry, is going to equal to the inverse sine of 4 over 6, and that's a button on your calculator that you can use. And once you do that in your calculator, making sure everything in brackets is in brackets, you will end up getting 41.81 ... So if I were to do this in 3 significant figures, I can leave my answer as theta is equal to, approximately is equal to 41.8 degrees. And that's my angle. So basically, if I had sine theta, in order to find the angle, I would use the sine inverse function. If I had cosine of theta is equal to the adjacent over hypotenuse. In order to find theta, I would use the inverse cosine on my calculator. And if I had the tan of theta, and that's equal to, based on our SOHCAHTOA, is opposite over adjacent. So theta is equal to the tan inverse of O over A. And you can always do that on your calculator and figure out what those angles are. So this is how you find angles, but SOHCAHTOA is so much stronger than that. It's so useful. So if you have a right angle triangle, again, I'm going to write SOHCAHTOA. And let's say you have a right angle triangle and you are trying to, let's say you have this angle and this angle is let's say 30 degrees, for example, and let's say you have one of the sides. It doesn't really matter. Let's say you have the hypotenuse. Let's say this is 20. And you want to figure out what these two sides are. Well, at the moment, you can't use Pythagorean theorem because in order to find Pythagorean theorem, you need a little bit more information, but you can use SOHCAHTOA. Well, how? Let's say we want to find the opposite side to our triangle. Well, we have the hypotenuse, we have O. If we look up here, we need O and H, and you can see O and H is right here, so we need sine. So we know that sine of our angle is always equal to our opposite over hypotenuse. So sine of 30 degrees is going to equal to my opposite side. I don't know what that is. I'm going to try to find it. And my hypotenuse, I do have that value, is 20. So in order to find that opposite side, we're going to multiply both sides by 20, and we're going to get 20 sine 30. And if we put that in a calculator, we will get 10. So that would mean that this side is 10 units. So now that we have that one, I'm going to use the same idea. I have my angle. Now I want to try to figure out this side, and this side is adjacent to my angle over here. So I have the adjacent. The hypotenuse is given as an exact value. That's what we're going to use. So adjacent and hypotenuse, that works with this ratio over here. So that's a cosine that I need. So in order to do that, I'm going to take the cosine of my angle is equal to A over H. So that's adjacent, what I'm trying to find. The hypotenuse is 20 and my angle is 30. Now to find adjacent, I'm going to multiply both sides by 20 and I'm going to get 20 cos 30. So in this step, we have multiplied both sides by 20. And I put that on my calculator, and I will get approximately 17.3 given in 3 significant figures. So this side here is approximately 17.3 units. So you can see how useful these things is. As long as you have a right angle triangle and you have one of the sides and you have one of the angles, you can find everything else based on this set of ratios. And that's why it is such an important tool when it comes to physics. Now, how do we use this in physics? I'm going to actually show you. It's used when we are using vectors. So let's say we have a vector which is going in this direction, and let's say this is a vector which is given to us as vector A is equal to 40 kilometers, and let's say its direction is given in east. So this is my east direction, this is my north direction, and I'm going to take that to be positive. So let's say it starts east, turns, let's say 30 degrees towards north. So that would mean that it starts this way, it turns 40 degrees this way, and its magnitude is 40. So we know that much. And in physics, sometimes we need to change a vector into its components. What does that mean? So the components have to do with a sign convention that we use. And in a lot of situations, we use east, north, sometimes x, y, and sometimes we might use different things, but let's say east and north are chosen here. So east is going in this direction, so this vector is going to have a component in this direction, which is going to be east, and it's going to have a north component, which is going in this direction. The components always add up to the vector. So let's think about the components here. In this one, the east direction is going this way, or horizontally. So the east component with vectors, it's going to start from the origin point here. It's going to travel in this direction, in the east direction. It's going to stop around where the head of the actual vector is. So this is going to be a component. It's going to be smaller. So this length is smaller than this one, but it's going to be a component of this vector in the horizontal direction. In the vertical direction, the north direction, we're going to start from this same point, or we can kind of start from here. It doesn't really matter. And we're going to connect it back to the head of the actual vector. So this component here is going to be AE. That's going to be in the east component, and this one is going to be the north component. Okay, excellent. So we have all of that information. Now we need to figure out what are those components? What are the actual values of the components? And then we can talk about the positive and negatives after as well. So I want to find AN. And so for AN, I'm going to use SOHCAHTOA. All right, SOHCAHTOA here. We got S, we got C, we got T. We want to find AN. So in this triangle, this is the hypotenuse. This is opposite to my angle, and this is adjacent to my angle. So AN is opposite, so that's what I'm trying to find. I already have the value for the hypotenuse, so I'm going to use opposite hypotenuse. I have to use sine. So let's do it. So sine of my angle 40 degrees is going to equal to the opposite side, which is the north component of my vector, and this is its magnitude, only the value, we don't care about the direction at the moment, divided by the hypotenuse, which has a value of 40. So we're going to multiply both sides by the hypotenuse, or 40, and we're going to get 40 sine 40 here for our value. Maybe I should have chosen a different angle, but that's okay. So 40 sine 40 here. And that's it. So as a shortcut, whenever you want to find a component which is opposite to your triangle, you can just multiply the hypotenuse by the sine of an angle. So sine for opposite. So whenever you want the components, you multiply the hypotenuse by the sine of the angle. So this is going to equal to approximately 25.7 in 3 significant figures units. Now let's talk about the east component here. For the east component, you can see that it's the adjacent side, and we have the adjacent, we have the hypotenuse. So adjacent and hypotenuse are given. We're going to use cosine. So cosine of the angle 40 is going to be equal to the east component divided by the hypotenuse, which is 40. And we're going to multiply both sides by 40 to get 40 cosine of 40 as our final answer. And that's going to be approximately 30.6. So a few things to notice. First of all, the hypotenuse is 40. So the components, if this hypotenuse is the biggest side, so the components need to be smaller, and they are. This one is 25.7, smaller than 40. This one is 30.6, smaller than 40. The other thing that you need to notice is that these two don't add up to 40, so you don't have to worry about that, because if they did, that would mean that these two are lying on the same plane, or the angle between them is 0. So those are the things that you need to focus on. And if you want to write the east component of this vector, then we know that its magnitude is 30.6. Its unit is kilometers, and it's moving so our positive east based on our sign convention is to the right, and this component is also to the right. So this is going to be in the east direction. It's going to be positive. And for our north components, if you want to write it as a vector, its magnitude is 25.7, unit is kilometers, and you can see that our positive convention is in the north direction going up. This is also going up, so it is positive, and it's going to be north. Let's do one other vector example. So I'm going to move this up, and I am going to draw the vector this time differently. Let's draw it in this direction, and let's give a different angle. Let's give this angle as, let's just give it as 40 degrees again, but this time we'll change this to 50 so that it's not as confusing. And I'm going to write the vector. This is going to be vector B, and it's going to be 50 kilometers, and it's going to start south. It's going to turn 40 degrees. It's going to go in the direction of west. And assume everything is 3 significant figures here, so that our final answer will also be in 3 significant figures. First thing we need to do to break this down into its components, so we're going to start from the very beginning. We're going to actually provide a positive sign convention, east and north. So we're going to move from the initial point down in the vertical direction, and that's going to be in this direction until we reach the head. So that's approximately here. So I'm going to do that. And then we're going to move from here and in the horizontal direction until we connect to the end. So this is going to be the east component, and this is going to be the north component. Note that we can do this differently. We can start from here and move east first, and then move south to get there. We just need to do 90 minus 40. This will be a 50 angle, and then we can do this exact same method, and it will work, and it will work great. Okay, let's find the vector quantity that represents the components in the east direction and components in the north direction. So for the east direction, first of all, we can see that our positive east is in this direction, right direction. However, this is going to the left. So first thing I'm going to do is I'm going to put a negative. And the negative and positive completely come from our sign convention, and we have chosen our sign convention to be this way. We could have chosen north this way and west as positive, and then we would have to put positive here. In this case, east, this is going west, so we have to put a negative. So, and this side over here, it's opposite to our angle, so we are going to multiply the hypotenuse, which is 50, opposite. I'm going to put SOHCAHTOA here again, SOHCAHTOA. We're using our hypotenuse and the opposite, so that's sine. So it's going to be sine of 40. And for Bn, to find that is adjacent. And so we're going to multiply our, actually first we need direction, sorry. So for our direction, Bn is going down. Our positive sign convention is up, so they're opposite, so we're going to use a negative sign. And to find its magnitude, we multiply the hypotenuse. Since this is adjacent and we have the hypotenuse, then we have to use cosine. So this is going to be cosine of 40. Put this in our calculator and we will get approximately the components in the east direction is negative 38.3. Unit is kilometers. And the sign convention that I've chosen says that this is in the east direction. And for Bn, this is going to be negative 38.3 approximately. Unit is kilometers, and my sign convention says that this is north. You can also change these, and you know that, well, first of all, make sure that it makes sense. So this is negative 38 in the east direction. So east is going this way, but ours is going in the opposite direction. That's negative. That makes sense. You can also express this as positive 38.3 kilometers west. Completely your choice. And for the next one, it is, let's see if it makes sense. It is going down in the south direction, but our value here says north, so it needs to be negative in the north direction or positive in the south direction. So this is the skill that we use to break down a vector into its components. Now, what if you were given the components and you were asked to tell me what is the actual vector? So let's do that. Let's have a new vector. This vector is going to have two components. It's going to have a component in the east direction, which is negative 4.2 kilometers. And this is an arrow, and it's going to have a component in the north direction, and that's going to be, let's give it 3 kilometers. And our east and north are indicated positive in this way. So this is in the east direction, and this is in the north direction. So now we are going to kind of look at how we're going to turn this into a vector. So I'm going to scroll here, and we can see that the east component and north component we have, we can use them and add them in order to get the actual vector. So I'm going to start off here, and we can see that we got the east component being negative 4.2 kilometers east. So our positive east is in this direction, so negative will be the opposite to that, so it will be going in this direction. And the magnitude of that is 4.2. And the north component is, you can see it's the up direction, that's the up direction. So I have to move up, so from here I'm going to go up by approximately 3. And that's going to be my north component. And the actual vector will start from the beginning and end right here. So I will connect them using a straight line. So now we can see the vector. The vector starts here, ends here. We have to find, in order to express it, we need a magnitude and we need a direction. And in order to get that direction, we need an angle. And I'm going to put a theta angle over here. So alternatively, actually, if you were going to do that, it doesn't matter whether you start with this or this. So if you started here from the original point, we would go up by 3 kilometers, and then we would go left in this direction, and we'll end up, this one would be 3 kilometers, this one would be 4.2 kilometers, and we would still have the exact same vector. We could just calculate a different angle. It's completely fine. You will get the exact same answer at the end, maybe just expressed in a different way, but it will be the correct one. Okay, so in this example also, I'm just going to change my number of significant figures. This is going to be 3.0, so that my final answer also has 2 significant figures. And okay, so I have the 2 components. To figure out this magnitude, I'm going to use Pythagorean theorem. That let's call this vector, let's call it vector, well, it is vector A. So the length of A, so whenever I want the length and I don't want to show the direction, I'll just write it without an arrow on top. So A squared is going to equal to 3 squared plus 4.2 squared. So A is going to equal to the square root of 3 squared plus 4.2 squared. It's actually a plus or minus here, but since this is the length, we don't have to worry about the negative. And once I put that on my calculator, I will get approximately 5.16. I'll just write it actually, 5.161395. And here, because this is my final answer, I'm gonna round it to 2 significant figures, and that's going to be 5.2 kilometers. Now, in order to find the angle over here, I'm going to use my SOHCAHTOA, so SOHCAHTOA, And we already have, let's use the exact values and not the one we just got. It's a little bit better to use that. So here we have our side. This is opposite and this is adjacent. Opposite and adjacent are done using tan. So the tan of my angle is going to equal to opposite. My opposite side is 3, and my adjacent side is 4.2. So in order to get theta, I'm going to take the inverse of tan using my calculator of 3 over 4.2, and that's going to be approximately 35.5 or 36 degrees. So to express my final answer over here, I have to go back and use my sign convention. So I know the magnitude of my vector A is going to equal to 5.2 kilometers. It's going to be approximately, actually, because I'm rounding my values. I can't say it's equal because it's not. And in terms of its direction, it's going to start here. It's going to go in the west direction, turn towards north. So west is going to turn towards north for an angle of approximately 36 degrees. And that is going to be my final answer over here. So meaning that if I had components of negative 4.2 and component of 3 kilometers north and this one in east, then the vector created from those components is going to be this. And in order to figure out the steps, again, sketch first. So sketch these two first, and then use Pythagorean theorem to find its magnitude, and use the SOHCAHTOA or trig ratios to find the angle. And once you have those, express your final answer. Your final answer is going to have the magnitude, it's going to have the unit, and it's going to have the angle. And angle expressed in terms of how your vector is set up. So those are kind of the procedure. I hope this video helps you if you have a little bit of problem about trig ratios and how they can be used in physics. And again, these are the basics. I'm not talking about how to add two vectors here. It's just one vector and how it can be expressed in terms of its components and how you can use its components to turn it into a vector.